project? Good? Learn something? Okay, so hope you had 2 days of rest. The second project is going to be released today. So it's actually going to be on finite volume, which is what we're going to be talking about today. Okay, so the equations we have been solving are mostly linear equations, right? So what a linear equation means is that if you have an equation, partial differential equation with certain boundary conditions, if you multiply the right-hand side of the differential equation by a factor of 2 and also multiply all the quantities you appear in the boundary condition by a factor of 2, the solution is going to be multiplied by a factor of 2, right? So that's also you have the principle of superposition. If you add up two solutions, the sum of the solution is still going to be a solution. So this is a linear differential equation. The advection diffusion equation, which we have been looking at, partial w, partial t, plus u times partial w, partial x, equal to kappa of partial square w, partial x squared. That's a typical example of a linear equation, right? So if you add two solutions to this differential equation, the sum is still going to be a solution. So what kind of differential equation would be nonlinear? How would you modify this equation to make it a nonlinear differential equation? Yes? WWX. So, right, so what you are suggesting is, what if I have a term that is w times derivative of w to x, right? So if you have a term like that, yes, it'll be nonlinear because, well, let's, for example, if we replace this term by this term, okay, instead of a fixed constant u multiplied by dw dx, if we multiply w by dw dx, or actually anything that depends on w, right, times dw dx, my equation is going to be nonlinear. So we don't even, let's just ignore the second derivative dissipation term right now. So let's just consider the equation dw dt plus u as a function of w. So now u is not a constant, times dw dx equal to, let's start with 0. This is a nonlinear equation. Why? Because if you have a solution w that satisfies this equation, I hate the flickering. Don't know. Okay, so if you have a w that satisfies this equation, you multiply w by a factor of 2. The first term, dw dt, is going to be, what's happening? Do you guys have any clue? I didn't touch anything. Okay, so the dw dt is, of course, going to be multiplied by a factor of 2 if you multiply w by a factor of 2. But the second term is not going to be multiplied by exactly a factor of 2, very unlikely, right? So dw dx is going to be a factor of 2, but like because u actually depend on w, the result is the equation is not going to be satisfied. I don't know what's happening. What? This is worse. Okay. All right, let's keep that for now. All right. Okay, so here's a nonlinear equation, well, so the first thing we look at is, can we solve this equation the way we have been solving differential equations before, using finite difference? No? Why not?
You can do it, but you will not obtain linear equations in terms of W. You have to write a matrix to solve that.
Okay, so what you pointed out is that the old way of forming a matrix doesn't work anymore. But here, actually, if I solve a time-dependent problem, right? So we use the matrix method to solve the Poisson's equation, a time-independent problem. So here, we actually just want to solve a time-dependent problem. We convert this equation into what? Into ordinary differential equations, right? And it actually doesn't really matter if we just ask OD45 to solve it, if it's linear or nonlinear. So maybe we can just try it in MATLAB to see what happens. How about that? All right. So let's just start by looking at the equation. Actually, let's just say U of W is equal to W. So this equation is called the Burger's equation, when the U, which denotes actually the speed of advection, right? So in previous classes, when U is a constant, a positive U means the wave is moving towards the right, a negative U means the wave is moving towards the left. And here, what we are saying is that now the speed of the wave actually depends on the solution itself. If the solution is large, the speed is large, and if the solution is small, the speed is small. And in particular, if the solution is negative, I have a movement towards the left, and if the solution is positive, I have a movement towards the right, right?